Welcome back, ladies and gentlemen. Here we go, looking at conservation of energy. And even more than that, we're going to start by looking at different types of energy. Comes in all shapes and sizes, right? And I'm sure you've heard some of these terms before, but it's worth going through this. As you know, we have already been looking at this thing called kinetic energy. And there's something else called gravitational potential energy. There could be energy stored in a spring, so I'll just say spring energy. Energy of heat and sort of, you might think of this as sort of general molecular motion, you could call thermal energy. Think about steam engines and whatnot. You could have chemical energy. Well, okay, the food you eat is how you get your energy. The energy to do things, to live, energy for your muscles to contract and your neurons to fire and all those things. That comes from the food that you eat. So there must be energy stored there. So you've got chemical energy, energy in the chemical bonds. And it's not just in food, there's energy in all chemical bonds. There's also this weird thing called rest energy. Okay, this is a weird one. We actually are not going to do much with that. So here's the deal. Let me give you a brief rundown of each of these things. Remember, kinetic energy is the energy of motion. Gravitational potential energy is energy related to the position of an object relative to gravity, so to speak. So we can just say energy of position. And that's one way of thinking of gravitational potential energy. Spring energy, you might compress or stretch the spring. So energy stored in a spring. Thermal energy, think about heat, right? Chemical energy, chemical bonds. And finally, rest energy here. Okay, rest energy, check this out. This is Einstein. E equals mc squared. Technically, I guess this is called your rest energy, but if you look into this equation and what Einstein was really doing, he didn't really write the equation like this. And more correctly, there's another term in the equation, and we got to change something in this term of the equation. Never mind any of that. We're not going to get into the theory of relativity. We are, however, going to look at a couple of these in some detail. They really matter to us a lot. First, I want to highlight the first three on this list, because those three things represent what's called mechanical energy. The thing about mechanical energy, though, is for our purposes, we're going to be ignoring spring energy. We're not going to get into springs, even though they're cool. We're going to focus on these two. That's where our emphasis will be. And it's really cool. It's going to be neat stuff. So we're going to look at mechanical energy with kinetic energy and gravitational potential energy. You'll usually hear me say just potential energy, but this is what I mean. Okay, so you recall for kinetic energy, this equation. Kinetic energy is related to the mass of the object, and it's also related to the square of the object's speed. Well, potential energy, gravitational potential energy, usually call it PE, or write a PE for short. This is equal to the mass of the object times acceleration due to gravity times how high an object is. So we can put an H there. How high an object is above some reference point. The reference point can be anywhere you want. It could be the floor, your height above sea level. You get to pick how, where you're starting to measure the height. But the thing is, when we combine these two, when we look at them together, that's what we're calling mechanical energy. That's the name. Mechanical energy. And we're going to use just a capital E for that. So you're going to see this, you're going to see these symbols, and of course you'll see these equations also. So kinetic energy, 1/2 mv squared. Potential energy, mgh. Now sometimes the h, sometimes is written as a y. Sometimes it's written as a change in the y. Sometimes it's written as a delta dy, which is something you've seen before. Okay, they all mean the same thing. They all will tell you the same thing. It's just how high something is above a reference point, above some level that you consider to be 0. Cool. Well, the thing is with these, if there's no net work being done, so if the net work is 0, if the total amount of work done is 0, then mechanical energy, remember E is mechanical energy, then mechanical energy is conserved. And this is a huge idea, very important idea. There's no work done on the object, or the sum of the work done equals 0, right? Then mechanical energy is conserved. What does conserved mean? Conserved really means that the value doesn't change. It's a constant amount. Okay. What this tells you, though, is since you remember that mechanical energy is equal to kinetic plus potential, well, could you interchange some of these? Could you take some kinetic energy and change it to potential energy and still have the same total? Yes, you could. Energy can change. This is also important to realize. Energy can change forms. And specifically for us, from kinetic energy to potential energy, or back. And if it does that, that doesn't mean the total has changed. Here's an example. Imagine you have some money, right? And you're going to keep this money in 2 different bank accounts. So you have bank account number 1, and you have bank account number 2. And let's say at first you put $100 into each account. So what's the total value? What are your total assets? Your total assets are $200. All right. Well, is it possible for you to move money from one account to another? Well, sure, the banks let you do that. And let's say you take $50 out of this one. That leaves you with $50 here. And you put that $50 into this account. You end up with $150 over here. What's your total? $200. Your overall amount of money hasn't changed. You could go extreme and say, I want all my money in one account and none of it in somewhere else in the other account. Your total is $200. You could get a little silly with it, keep $1 in one account and put $199 in the other account. Your total is $200, right? Okay. In this situation, your money is conserved. No matter where you put it, you still have $200. The total is unchanged. However, if you want to increase the amount of money you have, if you want that value to increase right there, then that takes work. You have to work and get a paycheck and you'll increase this amount, right? So if you want that to go up, you have to do work, right? Okay, now, if you want work done for you, that's different than you doing work. If you want work done for you, then what's going to happen? Well, you have to spend some money. You got to pay for that. So work done for you takes money out. work done for you. It requires money. You got to pay someone to do the work for you, so you end up with less. But you can see what's happening. Work is changing your total value. You can switch money back and forth between accounts all day long. Your total doesn't change. But you do work, or you have work done, and your total will change. We're talking about that very same thing with energy. Here we can say, without work being done, your money is conserved. Well, here, with no work done, then energy is conserved. Same idea. So, back to energy now, right? Kinetic energy and potential energy are just like those two bank accounts. As long as no work is done, either by you or for you, your total remains the same. So energy is the same as long as there's no work being done. So no work being done means net work is 0. That says net, I'm sorry. Net work is 0. Then mechanical energy will not change. So if there's no change in mechanical energy, then it equals 0. The change equals 0, right? No change. That's another way of looking at this. The mechanical energy remains the same. So, okay, we've got that, and I also want you to recall this. That the total energy, or the mechanical energy, is equal to the kinetic energy plus the potential energy, right? We already said that. We kind of showed that here. Or if we add those together, that's what we get. We get mechanical energy. This mechanical energy of the system is equal to the sum of the kinetic energy and the potential energy. Also, the mechanical energy will be constant, in other words, conserved, so long as no work is done on the system. You know, if you do work on the system, you add energy. And no work is done by the system, so that would be removing energy. So here, let's look at an example to make this a little more clear for you. Consider a ball dropped from a height of, let's say 2 meters. And the ball has a mass of 1.5 kilograms. Not terrible. So the moment it's let go, it isn't yet moving, so its kinetic energy is 0. And we can look at that. We can say, when you let go, the instant you let go, what's going on? All right, well, we can say kinetic energy is 1/2 mv squared. And the moment you let go is its initial velocity, but that initial velocity will be 0. It hasn't moved yet, but it's about to. So with a 0 velocity, you would get 0 joules of kinetic energy. What about its potential energy? Right, so these are initial values. I should add that. Its initial potential energy. Well, we can look at mass times acceleration due to gravity times height. And we can say, well, I know the mass, 1.5 kilograms. I know G is 9.8 meters per second squared. And I know H, it's 2 meters above the floor. So, 2 meters. Okay, when I do this math, I get an answer of 29.4 joules. It turns out that you get the same units, kilogram meters squared per second squared. It's still just joules. So there's my initial potential energy. You can think of potential energy as the potential to do something, but it hasn't yet done something. Okay, well, what about when it hits the floor? Let's look at that. Just when this ball hits the floor, what is the potential energy then? Oh, this will be a final value of potential energy. we just go, well, mgh. The interesting thing here, the mass hasn't changed and g hasn't changed, but h has. H is now 0. It is on the floor. Anything times 0 is just 0. So now the final potential energy is 0. That's important to see that. We had over 29 joules of energy before or when we let it go, and we have 0 potential energy now. It's an important question. Where did this energy go? It did not just evaporate or disappear. It had to go somewhere. Energy cannot be created or destroyed, only changed, only transformed into something else or moved somewhere else. Well, the answer to where these joules of potential energy went is they went into the other bank account, so to speak, right? The change in potential energy here is equal to a final potential energy minus an initial potential energy. Okay, well, that's fair enough. The final was 0, and the initial was 29.4. All right, cool. So this is lost potential energy. I mean, this basically is now a negative 29.4 joules, and it's lost potential energy. It's no longer in the potential energy bank account, right? So it must have gone into the other bank account. It must have gone into the kinetic energy account. That's where it ended up. So let's look at how that works. So again, I'll look at when we hit the floor. I'm sorry, when we let go. When you let go, let's look at the other bank account, the kinetic energy bank account. This is our initial kinetic energy. It's 1/2 m initial velocity squared. Well, what is our initial velocity? That is 0 at this time. Just when you let it go, it hasn't started moving, so you got 0 squared. Anything times 0 is 0. There is no kinetic energy in the beginning. Okay, but what about when it hits the floor? When it hits the floor. Okay. So we have a kinetic energy final. We know that that is 1/2 mv final squared. And remember, we had these 29.4 joules of potential energy that were lost. That's why it's a negative sign here. And we recognize they have to go into the other account. They went into the kinetic energy. So this is the other account. This is where the 29.4 joules went. Into that. So we would simply write the 29.4 joules here. That is our kinetic energy at the end when it hits the floor. Oh, by the way, we lost the minus sign because we're not losing kinetic energy, we're gaining kinetic energy, right? But there's more to it. This is something, this example where we dropped the ball, it's kind of a specific example. Let's look at something very general here. It's worth noting. All right. The real way, the actual way you should envision and look at conservation of energy. So here we go. Serious business, conservation of energy. And remember, E is mechanical energy. Here it is. Remember that when net work is 0, the change in mechanical energy is 0. In other words, there is no change in mechanical energy. No change means it's constant. So the initial amount of mechanical energy you have is equal to the final amount of mechanical energy that you have. That's it. Now, that's not all I'm going to write, of course. But if you can remember this, when energy is conserved, the initial equals the final amount. Then you've done actually quite a bit already. You've succeeded in recognizing a very important relationship. Okay, but what is this initial mechanical energy? It is made up of the initial kinetic energy and the initial potential energy. Those two things are combined in the mechanical energy. And it's the same thing for your final values. Your final mechanical energy is made up of your final kinetic energy plus your final potential energy. Remember, these are just the two separate bank accounts, and from before to after, your total value isn't changed. It's got to be the same. We're conserving your money, we're conserving this energy. So we can look at how to take energy from one account to another or back the other way, but the total has to remain the same. And you guys recall that kinetic energy is still 1/2 mv squared, potential energy is still mgh. So we could further break this down. 1/2 m initial velocity squared. Why initial? Because that's my initial kinetic energy. And here, mgh. And really it's initial height. And here, 1/2 mv final squared. Final because it's my final kinetic energy. And then mgh final. How high is it above your reference line at some other time, some later time? It might be zero height, right? So we can look at that and say, well, for the ball, in our example, this right here, this business is universal. It works for any situation where you can say energy is conserved. This is what you have to look at. You must start here and break it down like this. In our example, though, of dropping the ball, we see that there was no initial kinetic energy. There was just some initial potential, right? And at the end, there was final kinetic energy, but there was no potential energy. It had fallen to the floor, so H was 0. So you had no potential energy left. And also, quite interesting, look at what happens. We have mass on both sides. Mass ends up canceling out. And that's kind of curious, but it's nice in certain situations. Okay, so how does this look? I have to continue this on the next page, unfortunately. Okay. Well, I'm going to finish this calculation. I'm going to have a 9.8 meters per second squared. That's my G. I'm going to have H was 2 meters. And here I have a 1/2 m canceled out and final velocity squared. Check this out. I can actually calculate the speed of this ball right when it hits the floor. And when I get this going, turns out 6.26 meters per second. I'm able to calculate that speed. And in truth, it wasn't all that hard, right? This is hopefully going to start looking like this is an easier method to deal with velocity and define a velocity than the old equations we've been using. That's one of the benefits of looking at things from an energy standpoint, is a lot of these problems that we try to solve actually become easier. So to finish this off, I want to mention something. We can find the speed of an object by seeing how its energy changes from potential to kinetic energy. We could also find the height of a projectile, for example, something launched like this. We could find the height, its maximum height, right? If we know the initial kinetic energy. So there's an initial kinetic energy here. If we knew that, or maybe if we just knew mass and an initial velocity, we could find that H. No problem. Or, even more interesting maybe, we could even find the launch speed of a roller coaster like accelerator, where you start horizontally, you go way up and way back down, and it's just awesome. So your initial launch velocity there to get you up and over that really giant hill, you can calculate that as long as you know how high it is, right? And maybe there's some speed up here, and we can work that out. But you get the idea. Okay. So that's all for now. I want to keep this one less than half an hour, and we've done that. Thanks for watching. I will see you next time.